In order to extend the possibilities of the scientific investigation of the Electra laboratory, a new light source is under construction by the synchrotron storage ring. It is the FERMI at Electra, a fourth-generation light machine called free electron laser. FERMI at Electra will be working from 2009, and it will have unique features. It will be able to produce intense and short flashes of light of extreme pureness, capable of beaming and filming the dynamic behavior of matter. But how is that possible? To understand it, let's enter the first part of the FERMI at Electra, a tunnel nearly 200 meters long. There we meet a photoinjector, a device that shoots packets of electrons at a speed close to that of light. We follow now the path of these electrons inside the tunnel, a real race for energy. The electrons, here seen in small red spheres, pass into the tunnel through a sequence of electromagnetic fields represented in the simulation by colored arrows. Thanks to the thrust of the electromagnetic field, the electrons gain more and more energy, and we can imagine them as surfers who gain speed surfing on the waves. In the video, the increase of energy in the electrons is simulated by a change of color. The chromatic scale shown at the bottom of the screen allows us to read the corresponding energy level of the electrons at any time. At the end of this first section of the tunnel, the electrons, now represented by green spheres, have acquired enough power to take the next step, during which the bunch of electrons is more compact. But how can it do that? It passes through the bunch compressor, a sort of packaged magnet that compresses the length of beams of electrons arriving. The operations just described are repeated several times. The final result is the production of electron bunches, represented in light blue, that are shorter and full of energy. So far, the first part of FERMI at Electra. The door you are looking at now points at the transition to the second part of the machine, where the electron bunches pass through a sequence of magnetic devices that force them to follow an undulating path. In the first device, called modulator, the electrons encounter a laser wave, represented in the video by the colored serpentine. The interaction with the electromagnetic field of the laser creates a spatial modulation of energy in the electron bunches, well defined and linked to the features of the laser. In the next step, the energy distribution of electrons inside the bunch is transformed into a distribution of density thanks to the three devices in sequence. The electrons are then concentrated in subgroups, forming many smaller bunches. At this point, the new microelectron bunches enter the radiator, where the constant deflection of electrons from the rectilinear trajectory stimulate the emission of light. The electrons, represented in blue, and the light they produce, represented as a white trail, continue now in the same direction. The typical process of functioning of a free electron laser, like that of FERMI at Electra, is more visible at this point. Between the electrons and the light there is an interaction, a kind of dialogue, which allows the electrons to form themselves into a well-defined structure, dictated by the wavelength of light. In other words, between the electrons and the light there is a condition of harmonic oscillation, in which the light produced gains an increasing intensity. It is similar to what happens with the strings of a violin, that enter into resonance with each other and produce a more and more intense sound. At the end of the path, Leaving the magnetic field, the small bunches of electrons will have produced, in a never-ending game, extremely short and intense pulses of light. These pulses of light will finally be sent to the experimental room, where they will be directed on the samples to be studied, and will allow researchers to follow the evolution of chemical reactions through a series of ultra-fast shots, millionth of a billionth of a second, and of the microscopic world to the 100th millionth of a millimeter. With the light of FERMI at a letra, it will be possible to take snapshots that show the atomic and electronic state of a material, take pictures with a single flash of light of degraded samples such as the biological ones, or even excite the atoms to create new states of matter as the plasma hidden in the core of stars.